Okay, so let's talk about quantum physics right now. So if I asked you, what does the term quantum in quantum physics actually refer to? Would anybody be able to tell me? What other words do you see, or do you know in the English language? You can just leave them at the back for now. That's fine. Thank you. What other words in the English language have this in them? Because sometimes you can figure out what a word means by looking at other similar words. Quant. Quantity. Exactly. And that's the exact word I was looking for. Quantity. Quantity, and what does quantity mean? Yeah, a good way to say it is an amount, right? An amount of something. What quantity of eggs did you buy at the supermarket? What quantity of video games do you have in your video game library? What quantity of different shoes do you have on your shoe rack? And so on. So quantum physics uses the same root as the word quantity, and it simply means amount. Okay? And what we're saying here, what Bohr was saying, is that if you look at this model of the atom that we talked about just before, there's a specific amount or quantity of energy that exists between each of these levels. Okay? So the other day when I asked about shells and energy levels, okay, someone said that they were energy levels, and that's exactly what they are. And we also call them shells. And I just realized I drew these wrong. If you count, don't count this as one of the shells. Falling to the second shell is where you get your visible, and falling to the first shell is where you get your UV. So don't count this guy as a shell. I should have said that before. But whatever. So there's an amount associated with energy, and there cannot be any in-between amount. So in other words, an electron can never just be like halfway between two shells. It's either in one or it's in the other. This is kind of a surprising thing, right? It's not the way that we're used to really having, sort of nature work. Like for instance, if I have, say I have like an aluminum sphere or something. It doesn't have to be aluminum, but just some kind of sphere. And if I put it over a candle, right, and I let the heat go into it, on our level, we kind of get this idea that it doesn't matter. There's no such thing as energy levels. In other words, if I leave this on the candle for 10 minutes, it gets to a certain temperature. If I leave it on for 12 minutes, it gets to a certain higher temperature, right? And every, amount of time in between there has a relationship to temperature, right? It's probably something like this: time versus temp. Okay? That's not quantum, right? That's a constant relationship. There's any temperature is available for any given time. It's not the same for atomic energy levels, though. It's not the same for colors of light. You can't get every color of light out of a hydrogen atom because it can't exist between these two levels. It's quantized. There are quanta of energy in between each of these, which just means a quantity. So that's where this concept or idea of quantum physics comes from. There's a lot more to it, but this is one basic introduction. Okay? So when we draw Bohr models, you are doing quantum physics. So you can go home and tell your family, today at school, I did quantum physics, and you'll just blow their minds, right? So you can tell them, certified by the physics teacher at Westwood, I did quantum physics today, okay? So let's go back to the Bohr model, because we do need to talk about it and how it relates to chemistry. So the Bohr model and chemistry. Okay? Now, what is the most reactive metal group on the periodic table? We watched a video about them yesterday. Most reactive metal group. Good. Alkali metals. So let's pick the first two alkali metals, and let's draw the Bohr models for them, and let's talk about how their chemistry is what it is about them that gives them a reactive character. So lithium is 7. So it's got 3 protons, 4 neutrons. Okay. All right, so there's one of those shells that the hydrogen electrons were jumping up and down to. Well, sort of, in quotation marks, they kind of were. And if we were to, if we were to fire some energy into say a lithium gas in one of those tubes, it would give its own spectrum off, but it would be more complicated because there'd be more electrons jumping around. Okay, so there's lithium in terms of a Bohr model. Now, what do we know about a full shell? What is special about a full shell? We talked about it the other day. What elements all have full shells on their outer shells? Noble gases, right. So if you look at this, inside here, right, this shell is essentially the same shell that you would have if you looked at helium, right? Helium has 2 in its outer shell, that's full. This shell, however, can hold a total of 8, and it's only got 1 in it, all right? So what we say is this is the inner shell, and it's stable, right? It's stable. For the first shell, when it's full, you get stability, okay? The outer shell, though, is unstable. Okay, so this shell is really only at its most stable if you put 8 electrons in it, right? To get 8 electrons in it, though, we need a whole bunch more. I guess 7 more protons need to go in here, and then we're talking about a completely different element. All right. So let's just look at one more here. The next alkali metal, which is sodium. And let's look at sodium. It's got 11 and I think 23, if I'm not mistaken. So we got 11 protons. We got 12 neutrons. Now we have 2 stable shells. And we have an outer shell that looks identical to lithium's outer shell. This, as we talked about yesterday, is why they end up in the same family. Okay? This outer shell electron is hugely important. This gives the chemical character to the element. The inner shells are very unimportant when you're talking to a chemist. They're important for other reasons, but when you're talking to a chemist, they're not involved in reactions. Okay? So I'm just going to write that. Inner shells are not involved in reactions. Okay? They're not involved in reactions at all. It's the outer shell that is involved in a reaction. Okay? Now we said elements, atoms are stable at their most stable when you have a full outer shell. So if I look here, and you might have talked about this or touched on this last year, but if you look, if I were to take this electron away, if I were to remove it, what would I be left behind with in terms of shells? A full shell, right? A stable shell, all right? And same thing here. If I were to remove this outer shell electron, if I were to do that, I'd be left behind with a full shell, okay? Now take a look at 2 electrons and 8 electrons. Okay, now look up at the periodic table that's up on the wall there. If I go back one element before sodium, what element is one element before sodium? It's neon. What does neon's outer shell look like? What's in neon's outer shell? Eight electrons in its outer shell. So neon looks like this all the time. That's not right. So there's neon's outer shell. And look what happens. If I remove 1 electron off the shell of sodium, the next element up the table, 1 higher, right? Its outer shell exactly mimics neon's outer shell. Hence, it's become stable, right? So if I can get rid in some way of the outer shell electron here, I have stabilized a reactive element. Now the question is, how is it that these elements react in order that they lose their outer shell electrons? Well, let's look at that. So the easiest way, or I guess before we get too far into that, let's talk about what they might react with, okay? So what if I had, let's see, what if I had, let's talk about fluorine here, which is totally on the other kind of end of the spectrum. Spectrum, I shouldn't say spectrum. On the other end of the periodic table. So directly at the sort of the other end, the last element before neon, going from left to right, is fluorine. And fluorine is F, and it's got 9 and 19. So we'll quickly draw the Bohr model here. So 9 protons, 10 neutrons. It's got a full inner shell, and then how many in the outer shell? 2 plus what gives me 9? Yeah, 7. Okay. How many more electrons do I need to add in order to get this guy to have a full and therefore stable outer shell? So if there happened to be another element around with an available electron, it would love to party with this guy, wouldn't it? You know those people you just like to party with? The friends, right? You guys make a good team. You know, maybe you've got the fashion sense, and you know maybe they've got the wallet or something like that. Like you make a good team. Um, so anyway, if I brought something around here, right, with an available electron, and I think you probably know where I'm going with this. You know, guys like this and this would be awesome for this. So let's say we brought a sodium nearby some fluorine. So here's sodium. Sodium's got that. Sodium's got that. And then sodium has this one extra electron hanging around. If it were to pass its electron over to fluorine, right, that would satisfy both their needs, okay? I would be stable with my outer shell, and I would be stable with my outer shell, okay? So this is essentially the very basics of a chemical reaction between a metal and a non-metal, okay? So we're going to talk a little bit about how we fill outer shells. Before we do, it's a giant pain in the you-know-what to constantly be having to draw entire Bohr models. So there's a shortcut. We're going to learn a shortcut right now, okay? And it's called the Lewis dot diagram. So you've never learned about the Lewis dot diagram before? Okay, so before we can really get into what reacts how with what, let's make a shorthand way of doing this so we don't have to continuously draw Bohr models. So let's do Lewis dot diagrams. Let me know when there's 5 minutes left because I want to do a little quick experiment. Oops. Okay, so basically what this is a Lewis dot diagram. Lewis dot diagram. What they do is they just show the valence electrons. What's a valence electron again? Yeah, that's right. Outer shell electrons. Remember, the inner shell electrons are locked or closed up, right? They're in full shells, so they don't participate in reactions. So as chemists, we don't need to show them, right? We just need to show the electrons in the outer shell because they're the ones that are involved in reactions. So only valence shell electrons are involved in normal reactions. Okay, so how do we do this? Well, let's look at one row of the periodic table. Let's start with lithium. How many valence shell electrons are there on lithium? 1. So let's draw it. 1 valence shell electron. Next up is beryllium. How many does it have? 2. It's got 1 more. Beryllium. Then boron comes next. How many would it have? What do you think? I'll give you a hint. There's a pattern. Yeah, 3. Right? Remember, we started a new shell at lithium, so that's 1. And we add a proton, right? So we have to add another electron, so 2, then another proton, so 3. And I think you see where this is going. Carbon has 4. Nitrogen. Notice how I'm filling them kind of in order. Oxygen. I feel like I'm going to run out of room. Fluorine. And last but not least, neon. Now, neon doesn't really react, so, I mean, we can draw it off on its own. It's not going to be involved in any reactions that we ever talk about. Do you have a question? Reactions. Oh, it's just shorthand for reactions. So RxNS reactions. Sorry, I used some shorthand. I don't know if that's like common shorthand or my own. I'm not really sure. Somewhere I learned to write reactions like that. Okay, so that's Lewis dot diagrams. So let's just go back to what we showed before. Let's talk about fluorine. And let's talk about sodium. So if I draw a Lewis dot diagram for fluorine, 1, 2, 3, 4, 5, 6, 7 electrons on fluorine. Okay. How many electrons on the outer shell of sodium? 1. Just like anything that's an alkali metal, it only has 1. Okay. So with Lewis, we don't have to draw all the rings for Bohr. We can just go and by the way, the easiest thing to remember, the whole wide world, is just counting from left to right, skipping the valley, will tell you exactly how many valence electrons there are in any family. So 1 to the far left, 2 for the alkaline earth metals, 3 for the boron family, so anything in there, boron, aluminum, and so on. 4 for the carbon family, carbon and silicon, and germanium, and so on. 5 for nitrogen, phosphorus, astatine. 6 for oxygen and sulfur and selenium, and so on. And for the halogen, 7. And for the noble gases, 8, except for helium, it's got 2. Does that make sense? So if I bring these near each other, okay, fluorine will attract an electron in order to have a stable outer shell, and sodium will get rid of an electron in order to leave behind a stable shell. So these will tend to react in this way. Now, we're going to talk about ions tomorrow, but this is the very basic way that elements react. Now what will happen is these will create it's called an ionic compound. Okay? And it's where a metal ion, and don't worry, we'll talk about ions more, a metal ion and a non-metal ion bond. Okay, so that's a little heads up for where we're going with this. Okay, so today, in a recap, we reviewed the Bohr model, right? We learned where it comes from. We learned a new way to draw valence electrons, because as chemists, that's what's involved in reactions. Okay? Tomorrow we'll get more into what an ion is, okay, and how we can make ionic compounds. Does that make sense? Okay, I'm going to take that as a